Hello guys, and welcome to another calculus video. In this video we're going to be doing a quick live solve of questions 30 through 40 of Cambridge Integration B 2020 round 1. Someone just requested this, so I'm just going to go ahead and do it super quick. Probably going to be about an hour long video, and so going into this, first of all, I want to do a quick disclaimer. I have seen these problems before. I haven't actually sat down and solved them, but I did give them a glance just to see what I would be dealing with. So it's not entirely a live solve, but I haven't gone ahead and actually solved them yet. So I'm going to be going and doing that. And one other thing to keep in mind is that I'll be checking my answers afterwards just to verify that they're correct. But there was no answer key that I found, so I can't verify that all of these will be correct at the time of recording. I'm just going to do my best. So anyway, hope you guys enjoy the video, and let's jump right into it. So question 30 right here is pretty simple. We have question 30, integral from 0 to 2 pi of 1 over sine to the fourth of x plus cosine to the fourth of x dx. And whenever I see sine fourth plus cosine to the fourth, I always think sine squared of x plus cosine squared of x, which is just 1, and then I square it. So this equals 1, and it also equals sine to the fourth plus cosine to the fourth plus 2 sine squared cosine squared of x, right? Excuse the bad notation here. So this means that we can kind of solve right here, and we find that sine to the fourth of x plus cosine to the fourth of x equals 1 minus 2 sine squared cosine squared of x. And so we can go ahead and just substitute that in directly. So we get integral from 0 to 2 pi of 1 over 1 minus, and then I'm going to go ahead and substitute in the definition of sine of 2x, the identity here. It's going to be sine squared of 2x over 2. So we can go ahead and multiply on the top and bottom there. And we're going to get 2. And excuse my handwriting, sorry about that. Just doing it live, the handwriting's of course going to be a little bit worse. So we get 2 over 2 minus sine squared of 2x. And now there's a few different ways we can go ahead and look at this. What's the best way here? Well, let's go ahead and substitute u equals 2x just to make things a little bit simpler. What's going on with my pen here? U equals 2x, so we're going to get integral from 0 to pi of du over 2 minus sine squared of u. And now I really don't want to use Weierstrass function here, so I'm trying to think of a better way. Oh, let's multiply on the top and bottom by cosine squared. So we're going to get integral from 0 to pi of, or sorry, it's secant squared. So we're going to get secant squared of u du. Whenever you have only even powers rational function, go ahead and multiply by secant squared, and that's usually going to work out. And we're going to get 2 secant squared of u minus tangent squared of u. And we're going to get, we're going to do u, or I guess we'll do v equals tangent x. So we actually get a little bit of a split integral here, which is not very fun. So we'll split this up into integral from 0 to pi over 2, and integral from pi over 2 to pi, just because of the tangent function. So after v equals tangent x, we're going to get integral from 0 to infinity of dv over 2 v squared plus 1 minus v squared, plus the integral from pi over 2 to pi. So at pi over 2, we're looking at pi over 2 minus and pi over 2 plus here. So we're going to be going from negative infinity to 0 of dv over 2 v squared plus 1 minus v squared. That's not very fun. But anyway, we end up with the integral over r. I'll just write that. Integral from negative infinity to infinity of dv over, it's going to be v squared plus 2. Let me just check to make sure I did my math right. Yeah, v squared plus 2. So this is going to be 1 over root 2 tan inverse of v over root 2 evaluated at infinity and at negative infinity, or pi over root 2. And I'll go ahead and check that to make sure that's correct in post. All right, let's move on to question number 31. So question number 31 is going to be integral of square root 1 plus sine x over 2. So I don't really like this type of integral. It sometimes gets a little bit nasty with the square roots and the trigonometry, and also the integral that we're going to end up getting here is not going to end up working perfectly. So essentially what we want to use here is that cosine of x over 2 equals square root 1 plus cosine x all over 2. So we want this to be cosine x, right? So the first thing we're going to do is u equals x over 2, which means that 2 du equals dx. This is indefinite, right? Let me just make sure it's indefinite integral. Yeah, indefinite. So we're going to end up with 2 integral of square root 1 plus sine u. Then we're going to do u equals pi over 2 minus v, and then du equals negative dv. So we're going to get negative 2 integral square root 1 plus cosine v. And then we can just go ahead and divide and multiply by square root 2. So we're going to put square root 2 right there. And then we put the square root 2 inside of the square root here. So we're going to get all over 2, right? dv. And we're going to get negative 2 root 2 times the integral of, now this is just going to be cosine of v over 2 dv. Then integrating, we're going to get negative 4 root 2 sine of v over 2 plus c. And then now we just have to substitute everything back. So we're going to get negative 4 root 2 sine of, so this is going to be pi over 2 minus u, and then u was x over 2, so pi over 2 minus x over 2. So we're going to get pi over 4 minus x over 4, which just looks terrible. We could rewrite this here. X over 4 minus pi over 4, and then make this positive and plus c. And again, I don't like this type of integral because this expression for the integral will only be valid for certain values of x, because we did this substitution, this right here. We use this identity, and this really should be a plus or minus sign, because when we take the square root, we can have plus or minus. So not my favorite question, but this is a valid antiderivative for some domain. So let's move on to question number 32. So question 32. All right, so we have integral from 0 to 1 of ln 1 plus x, ln 1 minus x. I have a video on a very similar but much more complicated integral here. So we're just going to be using the exact same ideas as in that integral dx. I'm not sure if there's a better way to do this. There probably is, but I'm just going to use the same method. So we're going to abuse the fact that a plus b squared minus a minus b squared equals 4ab. Now, in this case, a is just this, and b is just this. So we get integral from 0 to 1 of 1/4 ln 1 minus x squared. Is this all squared? Yeah, I think that's squared as well. Yeah. And then minus ln squared of 1 plus x over 1 minus x. All of this dx. Maybe this won't be as simple as I thought. All right, so for this one right here, we're going to try x squared equals u. And that means that, no, that's not going to work, is it? Huh. Let's see how we can do this. Oh, maybe it will work. Okay, let's give it a shot. So after x squared equals u, x equals u to the 1/2, and 1/2 u to the negative 1/2 equals dx. We're going to get 1/8 integral from 0 to 1, u to the negative 1/2 ln 1 minus u, ln squared 1 minus u du. Minus, then this is just an expression for inverse hyperbolic tangent. So actually we're going to have integral from 0 to 1 of inverse hyperbolic tangent of x, which I think is cool. And this is all squared dx. So for this first one right here, we're going to do, we're going to replace u with 1 minus u. So we're going to get 1/8 integral from 0 to 1 of 1 minus u to the negative 1/2 times ln squared of u du, just after u goes to 1 over u, minus, now we're going to go ahead and substitute x equals tan h of v. Why not? V works. So we're going to get v is going to go from 0 to infinity, and we're going to get v squared hyperbolic secant squared of v dv. And we're just going to proceed from here. So for this one right here, we're going to use the beta function. I'm not sure if this is the most efficient method because, again, I just took a peek at these integrals right now. So we know that integral from 0 to 1 of u to the m minus 1, 1 minus u to the n minus 1 du equals gamma of n, gamma of m over gamma of m plus n. So we're going to take the partial derivative here with respect to m. So we're going to get integral from 0 to 1, u to the m minus 1 ln u times 1 minus u to the n minus 1 du. Partial derivative with respect to m, so we get gamma prime of m, gamma of n over gamma m plus n minus gamma of m, gamma prime of m plus n, gamma of n over gamma squared of m plus n. Sorry that my m's and n looks so similar, but I promise I will get the right answer at the end here. So we're going to take the partial derivative again with respect to m. So we're going to integral from 0 to 1, u to the m minus 1, ln squared of u times 1 minus u to the n minus 1 du equals, oh, this is going to be really nasty. All right, there definitely has to be a better way to look at this. Let's take a look. Okay, well, let's see what happens if we substitute u equals 1 minus x. We get integral from 0 to 1 of ln 2 minus x times ln x dx. This looks a little bit nicer because we can rewrite this as the integral from 0 to 1 of ln 2 ln x plus ln 1 minus x over 2 ln x. Yes, this is definitely the more intended solution right here. Sorry about all that tangent that that I went on. So integral from 0 to 1 of ln x is just negative 1, so we're going to get negative ln 2 right here, plus integral from 0 to 1 of the sum from n equals 1 to infinity. I'm going to throw a minus sign in front of here. X over 2 raised to the n power all over n times ln x dx. Then integral from 0 to 1 of x to the n ln x dx equals negative 1 over n plus 1 squared. So we're going to get negative ln 2 minus sum from n equals 1 to infinity of 2 to the negative n over n times n plus 1 squared times negative 1. Okay, that looks actually way, way worse than what I had before. Let's take a look. So let's do partial fractions on this first of all. So we're going to have negative ln 2 plus sum from n equals 1 to infinity. And then we're going to get 2 to the negative n times 1 over n minus 1 over n plus 1 squared. And then let's figure out what the other term is going to be. I'm just going to do this in my head super quick. I'm guessing we're going to have minus 1 over n plus 1. And let's just go ahead and check to make sure that works. All right, I'm pretty sure that works. I'm not entirely certain. But anyway, this and this are just going to give us natural log terms. And this is going to give us a term involving Li2 of 1/2, which is not fun, but it is a known value, so I'll go ahead and sub it in. So we're going to get negative ln2 plus sum from n equals 1 to infinity of 2 to the negative n over n minus sum from n equals 1 to infinity, or I'll actually go from n equals 2 to infinity, 2 to the negative n over n. Actually, all multiplied by 1/2 right here. And then we're also going to be subtracting sum from n equals 1 to infinity, 2 to the negative n over n plus 1 squared. So overall we get negative ln2 plus, or actually minus, ln 1 minus 1/2 plus 1/2 ln 1 minus 1/2, and then minus whatever the first term of this was going to be, which is just 1/2. And then this right here is going to be based on the dilogarithm of 1/2, which is really, really nasty and a very difficult calculation. So I'm assuming that it would just be given for this competition. Yeah, so the answer to that is, so we're going to be subtracting, we're going to just do that. So we're going to end up with 2 times the dilogarithm of 1/2 minus that first term again. So the first term is when n equals 0. So yeah, something like that. I'm sure I made a mistake on this question, so I'll come back to it later and let you guys know what the actual answer is. But let's go ahead and move on to the next question and not worry about it too much. So the next question here is going to be question 33. We have integral from 0 to 1 of inverse tangent of 1 over, let's see, x squared minus x plus 1. So in this situation, what we're going to be using is tan inverse of a plus b over 1 minus ab equals inverse tangent of a plus inverse tangent of b. And in this case, a and b, as you probably have already guessed, we have this 1 already here, so we just have, a is going to be x and b is going to be 1 minus x. And that will give us this expression right here. So we actually have integral from 0 to 1, tan inverse of x minus tan inverse of x minus 1 dx. And notice this tan inverse x minus 1, or actually we had 1 minus x, right? Plus 1 minus x. So notice that these two are the same integral because of the because if you substitute u equals 1 minus x, you'll get both of these equaling each other. So we could just go ahead and erase this and multiply everything by 2. Then the integral of inverse tangent is really straightforward. So we're just going to end up with, I guess it's going to be 2 times pi over 4 plus ln 2. So pi over 2 plus ln 2. Just integration by parts. All right, next problem. This one's kind of silly. We have indefinite integral of e to the x plus e to the x in the exponent there. So here we just have this, right? So we could just do u equals e to the x, and then du equals e to the x dx. So we just end up with integral of e to the u du. And so our answer is e to the x plus c. I believe this has been used in MAT integration B a few times, so I recognize it. All right, now this one's kind of fun. We have integral from 0 to pi of inverse tangent of 3 to the cosine x dx. So with this, whenever you see really goofy looking stuff that looks completely unsolvable, just try King's property. So after u equals pi minus x, we get integral from 0 to pi of tan inverse of 3 to the negative cosine u, because cosine pi minus u equals negative cosine u du. So this is I, this is I. So if we add these together, we get that 2I equals integral from 0 to pi of tan inverse of 3 cosine x plus tan inverse of 1 over 3 to the cosine x dx. And then we have that tan inverse of x plus tan inverse of 1 over x equals pi over 2. So overall, our answer, 2I equals pi squared over 2, and I equals pi squared over 4. All right, so next up, oh, this one's kind of goofy. We have indefinite integral of x over x squared plus 4, x to the 4th plus 4, sorry, dx. I'm not sure why this is here. It's just u equals x squared, and we get integral of 1/2 du over u squared plus 4. And that just becomes 1/4 inverse tangent of x squared over 4 over 2, sorry, plus c. Wait, is that correct? If I differentiate that, do I get back the original function? Let me just check. Yes, I do. So that's the answer right there. This was, oh, sorry, I haven't been saying the question numbers. This was question 36. On to the next question. Question 37. Should be getting a little bit more difficult now. Yes, now we have integral of dx over root 1 minus x plus, what is this? Oh, sorry, root x minus 1, not root 1 minus x. X minus 1 plus root x minus 1 cubed. So obviously, u equals root x minus 1. And after we do this, we find that du equals 1 over 2 root x minus 1 dx. So we end up with 2 integral of du over 1 plus u squared, which is just 2 arctangent of square root x minus 1 plus c. All right, on to question 38. All right, this one's interesting. We have integral from 0 to pi over 2 of cosine x over 2 minus 2, 2 minus sine 2x. So this is very similar to an integral we did earlier that ended up with sine of 2x, as you guys may remember. This one's a little bit different. So the way I like to do this kind of thing is actually a little bit interesting. So what I'm going to do is I'm going to sub. Wait, does that even help me if I do that? Yeah. So what I'm going to do is I'm going to substitute pi over 2 minus x. So this is I. And then I'm going to take I also equals integral from 0 to pi over 2 of sine x over 2 minus sine 2x. And that's after doing u equals pi over 2 minus x. I end up with the cofunction on the top, and then sine of pi minus 2x is the same as just sine of 2x. Now I'm going to add these two together, and it looks kind of weird because now I have 2I equals integral 0 pi over 2 of sine x plus cosine x, which usually is not very good, but luckily we have some very, very cool identities that we can use to deal with this. And I just think this is so cool because this pops up all over the place. So we have sine x plus cosine x equals square root 2 sine x plus pi over 4. Crazy, right? So we can go ahead and substitute that in. And we get that 2I equals square root 2 integral from 0 to pi over 2 of sine x plus pi over 4 all over 2 minus sine of 2x. And the reason we wanted to do this is because now we can go ahead and substitute u equals x plus pi over 4. And after we do that, we get square root 2 integral from pi over 4 to 3 pi over 4, right? Sine of u over 2 minus. Now on the inside here, we're going to get sine of 2 times u minus pi over 4, which is the same as 2u minus pi over 2. However, sine of anything minus pi over 2 is actually just the same thing as negative cosine of that thing. So we're actually going to end up with plus cosine of 2u. And how did this help us? Well, cosine of 2u actually has a really nice identity. We're going to go ahead and substitute it in. We're going to rewrite this as 2 cosine squared of x minus 1. And now, what we can do is we can actually substitute u equals cosine x, and it works out very nicely. So after u equals cosine x, we end up with square root 2 integral. Oh, wait. Do we have a problem here? Huh. No, it's okay. We end up integrating from, so we end up integrating from 1 over square root 2 to negative 1 over square root 2, but we're going to end up flipping that because of the negative sign of the differential up here. So we're going to end up with negative 1 over square root 2 to 1 over square root 2 dv over 1 plus 2v squared. And now we just integrate directly. So we're going to do root 2v equals alpha, which means that root 2 dv equals d alpha. And we just end up with integral from, what is it going to be, minus 1/2 v alpha equals root 2v. Oh no, it's just going to be negative 1 to 1. Negative 1 to 1 of d alpha over 1 plus alpha squared. So we get that 2i equals this, which means that 1i is just going to be pi over 4. One last problem in this video, and that is going to be question number 40, the final question. And that question is integral from 0 to, oh, this is actually a really famous integral right here, looking at it. um, natural log of secant squared of x minus 2 over tangent x minus 1. So immediately we're going to see this and we're going to convert it to tan squared of x plus 1. So we end up with integral from 0 to pi over 4 of natural log of tangent squared of x minus 1 over tan x minus 1. Just go ahead and cancel those factors. We end up with integral from 0 to pi over 4 natural log of 1 plus tan x. And now in order to solve this, we're going to use King's property. So note that using the angle addition stuff, we get that tan of pi over 4 minus x equals 1 minus tangent x over 1 plus tangent x. So once we do King's property, we end up getting, this is I, right? So I is also equal to integral from 0 to pi over 4 of ln 2 over 1 plus tangent x. Oh, I just messed that up. Here, I'll fix that. 1 plus tangent x dx. And then adding those two together, we find that 2I equals integral from 0 to pi over 4 of ln 2 dx. Or I equals pi over 8 ln 2. And that's number 40. And that's all the problems. I will go ahead and check my answers, and you can edit in anything that may have been wrong. But anyway, I hope you guys enjoyed this live solve session. And yeah, I hope you guys, I hope this helps out whoever I made this video for. I don't really remember exactly. And yeah, happy solving, happy integrating, B. See you next time.